Good morning, good afternoon, good evening or good night, whenever and wherever you are watching. Thank you for your interest in my presentation on how our coordinated development of tubes and optics generates new possibilities for X-ray analytics. This is my first presentation on a virtual conference like this, and as Incoatec also strongly supports all efforts to fight the pandemic, I'll be giving this talk whenever possible from home. So enjoy this pre-recorded talk, but nevertheless feel free to contact me or my colleagues anytime if you have further questions or want to find out what we can do for you with our broad experience in X-ray analytics. But now I'm going to start this home office edition of my talk from home. Welcome to my home office. My name is Moritz Schlie. I'm a physicist working as a project manager in R&D at Incoatec. Today I will talk about new possibilities for X-ray analytics by coordinated development of tubes and optics, for us, but especially for our customers. Not even 2 decades ago, scientists of the GKSS Research Center and international manufacturer of scientific instruments Bruker joined forces. They combined their competencies in multilayer X-ray optics and X-ray analytics in science and industries and founded Incoatec. The original core competency was X-ray optics, which we will now have a closer look at on site. Incoatec stands for Innovative Coating Technologies because originally we were founded to make multilayer X-ray optics. They are produced in sputter facilities like those next to me. As X-rays penetrate matter, building X-ray optics is not trivial. Only a small fraction is reflected on surfaces, though there needs to be many surfaces stacked in order to reflect a noteworthy amount of X-rays. Additionally, the thicknesses of those layers as well as the incident angle need to be adjusted according to the X-ray wavelength to interfere constructively according to Bragg's law. The shape of the coated substrate as well as the spatial change of layer thicknesses allow to build optics to reflect, to focus, to paralyze, and all of them have the characteristics to monochromize X-rays. Such optics can look like this. Montel optics, Goebel mirrors, XRF monochromatizers. Our engineers are able to define coating on the nanometer scale extremely precisely. The layer thickness variation must be 0.05 nanometers accurate over a length of 15 centimeters. This would correspond to a motorway with 0.5 millimeter deviation per 1,500 kilometers. On my way to work home, I fortunately have much less kilometers to go, but the height deviation is certainly way bigger. Especially if I set up my home office at this nice beach at the river Elbe near the Incoatec headquarters. Incoatec's portfolio broadened when we realized that many customers were not interested in buying the nicest X-ray optics, but in getting the nicest X-ray spot. So we combined our Montel optics, for optic focusing X-rays in 2 dimensions with an X-ray tube, a high voltage generator and mechanical housings for easy alignment. This Incoatec microfocus source, IMUS, became our VIP, our very important product, and many people associate Incoatec mainly with the IMUS. So the marriage of multilayer optics and X-ray source were the kick-off for the IMUS success story. In order to launch the IMUS, Incoatec acquired new competencies in the fields of mechanics, electronics and application, which allowed us to offer tailor-made X-ray solutions for our customers. These include, for example, upgrades of existing systems with our IMUS or standalone setups, including safety systems. So, let's have a look at the lab. Welcome to the lab. Here we can see some IMUS in action. As the IMUS is traditionally air-cooled, features a short warm-up time and no moving parts, it offers a very stable beam in flux and position, a long lifetime and needs no maintenance. This also leads to low costs of ownership. Furthermore, it is easy adaptable to all common goniometers and more. Our application and service engineers will be happy to discuss your individual demands and implementations as upgrades or special engineering solutions. Typical applications are single crystal diffractometry or small angle scattering and more. As the pandemic ain't over yet, it's time to work from home again. I've chosen to set up my home office directly at Hamburg Waterkant, the coastal line of Germany's second biggest city and its biggest harbor. Incoatec is situated half an hour outside of Hamburg and belongs to its metropolitan area. When talking about the IMUS, we need to have a look at the main parameters for the combination of multilayer optics and microfocus sources to achieve a collimated or focused high brilliance X-ray beam. While our well-established Montel optic defines the divergence, the focal spot size and focal distance, there's a second major part of the overall microfocus source, the X-ray tube within here. The tube specifies wavelength, brilliance and the anode spot. So together optics and tube define flux and flux density. Keeping this in mind while we are heading back to Incoatec Tube Factory, it is obvious why we started designing our own tubes to obtain full control on all major parameters of our IMUS microfocus source. At Incoatec, we reached the next level with the IMUS when we started to design and build our own X-ray sources. A unique microfocus X-ray tube optimized for crystallography allowed to further increase the flux on the samples. Most microfocus tubes on the market were designed primarily for radiography. Radiography features high takeoff angles in order to preserve resolution over a wide field of view. Diffraction does not need a wide field of view. It only needs intense X-rays. So Incoatec acquired competencies in order to manufacture and design X-ray tubes. X-ray tubes need a combined understanding of high voltage, insulation, cooling, vacuum, electron optics, and cleanroom experience. Having these in-house allows a further pushing of the boundaries and the development of custom-tailored tubes for the IMUS and beyond. Beside the aforementioned takeoff angle, further improvements included the electron optics, but also the anode cooling leads to a higher power of the whole system. To achieve this, we reduced the thermal bottleneck by optimizing heat dissipation by successfully making use of the extraordinary high thermal conduction of diamond. The best way to show the achievements of recent IMUS designs is to have a short look where we came from. In 2006, Incoatec launched the IMUS, the Incoatec microfocus source copper, for biological crystallography and small angle scattering. And that is where we start our short walk along the IMUS timeline. In 2007, the IMUS molybdenum for chemical crystallography, and in 2009, the IMUS silver extended the spectrum. Literally. Silver is especially challenging due to its high energy and thus demanding even thinner multilayer layers. Behind the scenes, our scientists and engineers were working hard to optimize optics and more. And finally, in 2011, the next generation, the IMUS High Brilliance, or the light of day. It offers up to 60% more intensity and new target materials, among other improvements in ease of use. 2015 became another important year for Incoatec. We launched the new IMOS 3.0 for latest Bruker D8 systems. This next generation microfocus X-ray source offered a further intensity increase of at least 30% and is the first source featuring the newly introduced Incoatec X-ray tube, IXT. This very first coordinated development of tube and optics opened the door for new possibilities for X-ray analytics that become obvious when we reach the launch of the unique microfocus source IMOS Diamond Copper with diamond hybrid anode in 2017 and of the IMOS Diamond Molybdenum in 2018, both being able to reach and outperform even rotating anode setups. See the dashed lines. The output of the IMOS Diamond is much more stable in time than that of a rotating anode. All these developments were accompanied by permanent enhancement of the types of optics and tubes we are able to offer, and we will continue along this road. So last year we were able to celebrate 1,000 installed IMOS systems. I want to show you some exemplary applications of our IMOS. IMOS microfocus sources can be used in archaeometry and scientific studies of artworks to reveal elemental composition by micro-XRF techniques or material structure by diffractometric studies. Such studies are non-destructive, yet allow extensive material analysis and sometimes even unveil hidden layers underneath the visible surface or provide information on the aging of colors and how to preserve or restore them. This picture shows an IMOS shooting at an artwork by Van Gogh. The setup is part of the studies by Professor Janssen and his team. Furthermore, IMOS sources can be used at synchrotrons during downtimes to prepare for the next beam time. It allows to adjust your setup with X-rays or even use our setup for measurements. The closest IMOS is located just a few steps away from the Incoatec premises on the grounds of the Helmholtz-Zentrum Geesthacht. With their program Advanced Engineering Materials, nanostructured materials are developed for hydrogen storage, therefore using a Bruker diffractometer with an IMOS for testing the materials. The scientists have now developed a new chemical system for storing hydrogen in a solid compound and releasing it fully reversible. The new material opens up excellent perspectives for long-term usable energy storage. But now, let's do what scientists can do best: practice social distancing. The global virus crisis caused many of us to work from home, or wherever the risk of endangering colleagues or anybody else is low. The picturesque old town in the background is the city of Lüneburg, also roughly half an hour away from Incoatec, and choosen hometown for some colleagues who like to live in a city but consider Hamburg too big. And it might be more than a rumor that some of our projects have been inspired in Lüneburg's nice pubs in the medieval center. As Incoatec was always characterized by its flexibility and openness to special demands of their customers, it will be of no big surprise to you that this is also valid for our tube development. So here is a first insight in Incoatec's X-ray tube activities beyond IMOS. These examples show customizations of our tubes to adapt them to totally different systems and applications. One nice example is this tiny friend here. Not even the size of a pen, yet a complete X-ray tube. It can be used to ionize gases in various setups, but there are also totally different applications. X-rays to go! The iX Mini is a portable plug-and-play miniature X-ray source as a non-radioactive detector calibrant. The iX Mini can be used for performing reliable flat-field calibration, making fluorescent metal foils and calibrants based on radioactive isotopes obsolete in your lab. With the iX Mini, this calibration can now be done autonomously, even when there is no other X-ray source available, for example during downtime periods at synchrotrons. It's also a simple and easy to use source for the regular checks of your radiation detection system. Another customer need-driven development was our tube for Beatrix, the Beam Expander Testing X-ray Facility. Here, our tailor-made X-ray tube with adjusted spot size, a titanium target for radiation in the single keV range, and a custom interface is used as source in a complex system for testing hundreds of mirror modules at the Athena X-ray telescope, which is expected to be launched into space in 2031. I'm heading back, working from home, pandemic style, and we reached the end of this presentation. Today we presented how our history of offering solutions driven by the needs of our customers led from multilayer optics to complete microfocus solutions and now coordinated development of tubes and optics. We demonstrated how this opens up new possibilities for X-ray analytics and beyond. The Incoatechies are there to support your project in X-ray analytics and beyond, even when pandemic times reduce our on-site presence. Thank you for watching and feel free to contact us to find out what we can do for you. Stay safe.